We'll move right along to the acid-base reactions. And this acid-base reaction is when a hydrogen ion is transferred from one chemical species to another. That's the usual definition of, and this is known as the Bronsted-Lowry type of definition. An acid is a substance that will dissolve in water to yield a hydronium ion, H3O+. Hydrochloric acid is a strong acid, so when HCl is put into water, what happens is it forms the chloride ion and this hydronium ion. This acid-base reaction occurs when the H+ is transferred from HCl molecules to the OH molecule. When hydrogen chlorine gas dissolves in water, it reacts with the acid, transferring protons to the water molecules to yield the hydronium ions and the solvated chloride ions. Okay, just what we have right here. Virtually every HCl molecule that dissolves in water will undergo this reaction. In other words, it's completely dissociated from its initial molecule. Acids that completely react in this fashion are called strong acids. Examples are HBr, hydrobromic acid, hydrochloric acid, hydroiodic acid, nitric acid, perchloric acid, and sulfuric acid. Weak acids are compounds that behave and only react partially in water. A large majority of dissolved molecules remain in their original form, and only a relatively small amount of hydronium ions are generated. These would involve acetic acid and many of the other organic acids. Only about 1% of the acetic acid molecules are present in the ionized form, right here, and this acetate form right here. The use of the double arrow here denotes a partial reaction, okay? So it's at this side is in equilibrium with this side. It hasn't all gone over to the other side. Okay, so this is again also an example of an acid-base reaction. A base is a substance, according to the Arrhenius and also the Bronsted-Lowry definition, yield hydroxide ions, OH. The most common bases are ionic compounds composed of an alkali or an alkaline earth. In other words, group 1 and 2 on your periodic table. Potassium hydroxide, right here, sodium hydroxide, calcium hydroxide, barium hydroxide. These bases, along with other hydroxides, completely dissociate in water and are considered strong bases. And so this right here completely dissociates from this as a solid into this and this as a two ionic species. This process is a dissociation or a physical process, not an acid-base reaction. Okay? Some compounds produce hydroxide ions when dissolved by chemically reacting with water molecules. For example, these are usually classified as weak bases. For example, ammonium. Ammonia, when it's put into water, transfers a hydrogen ion to the ammonium to form ammonium instead of ammonia, and it has then this hydroxide in solution. And you'll notice again the back and forth arrows here indicated that this is at an equilibrium where there are some of each of these species at any one time. It's not completely all on one side or completely all on the other side. A neutralization reaction is a specific type of acid-base reaction in which the reactants are an acid and a base, and then the products are a salt and water. If you have magnesium hydroxide and you put that into a HCl solution, you're going to get a salt, magnesium chloride, and water. So magnesium chloride is a salt. So this ion and this ion are the ones that form the salt, and the H and the OH form the water. So an acid plus a base gives you salt plus water. That's a neutralization reaction. Okay? You can also see that this would be a double displacement as well, because this joins up with this, and this joins up with this. So in these, we have chemical equations that they have to be balanced. If you're doing it in terms of gases, you can do the same type of thing, but it's at a particular temperature and pressure. What you're going to be doing is you're going to have the same number of molecules, right? So these are always based upon the carbon 12, right? So 1 mole of a substance contains 6.02 times 10 to the 23rd molecules, atoms, ions, whatever. So this is 1 mole of a substance. And that gives us an easy way then, when we have a balanced equation, to then look at things in terms of from their molecular weight. That would, and then put in terms of grams, that would give us a number of moles that we have there. So 1 mole of carbon-12 atoms is defined as having 12 grams, okay? And that's a way to relate what happens on the microscopic scale to what happens on the macroscopic. We can weigh grams. We can't weigh out atomic mass units. Okay, so the gram atomic weight is the mass in grams equal to the atomic weight. The gram formula weight is the mass in grams equal to the formula weight. And the gram molecular weight is the mass in grams equal to the molecular weight. So each one of them is going to have 6.02 times 10 to the 23rd of that species present, that number, okay? So there's lots of ways to use this. You can look at the molar ratios of the reactants and products. You can look at the molecular ratios of the reactants and products, or the mass ratios of these. So you can have 3 molecules of this forming 1 molecule of this, plus 1 molecule of this forming 2 molecules of this. Or 3 moles of this, 1 mole of this, 2 moles of this. Or 6 grams, because it's 3 times the 2. 28 grams, because the n times 2 is 14 times 2. That's for 28. And this is 14 plus 3 is, This is, 14 plus 3 to give you 17 times 2 gives you 34. So 3 ways of looking at that equation, and you can do it either in terms of grams, moles, or numbers of molecules. These last 2 will be the ones that we'll primarily be working with. And essentially what you will now have is the reaction stoichiometry. A balanced chemical equation provides a great deal of information in a very succinct form. These chemical formulas provide the identity of the reactants, which molecules or ions are what you have there, and the products involved in the chemical change. The coefficients provide the relative numbers of those, and as long as you have a balanced equation, you have a quantitative relationship then between the amount of reactants and the amount of products, and this is called stoichiometry. So the concept is similar to the concept in food preparation. If you're at home there and you're making 8 pancakes, and the recipe calls for 1 cup of pancake mix, 3/4 cup of milk, and 1 egg. You can write this as these are your initial materials, and this is what you hope to get out of it. Now, what you can do is, if you have somebody else with you as well, you want to say, how much do you need if you want to make 24 pancakes instead? So 1 egg is used for 8 pancakes. So 24 means that you would need 24 divided by 8, or 3 eggs. And you can do it for each one of the different ones. 24 here would be 24 times 3 divided by 4. So divide this by 4, and you get 6 times 3. So that would mean that you would need 3 cups of milk. I'm sorry, you get 3, yes. 24 gives you 6 times 3 is 18. 18 cups of milk, and then you would need, for 8, you would need 3 cups of the mix. So balanced equations are used in a similar fashion as the recipes. As a matter of fact, a lot of chemists do quite well in the kitchen in terms of cooking up new recipes and things to eat. Not all of them are successful, but at least you know what you don't want to try the next time. So from a balanced equation, you can determine the amount of reactant required to react with a given amount of another reactant, and the amount of reactant needed to give an amount of product. Okay? And that's where those coefficients come into play. And remember, you only make certain that the coefficients are balanced. You never work with the subscripts. So here you have 1 of these giving you plus 3 of these giving you 2 of these. So the stoichiometric the ratio shows that it's a 2 to 3 ratio for this to this. Okay? So you can do this in that ratio. It can be moles or it could be grams. Dozens, I don't know anybody would do it with. Well, it's not grams. It has to be grams based upon that molecular weight. So you can't just do 2 grams of this. It has to be 2 moles. So you take the molecular weight of this times 2, the molecular weight of this times 3. Okay? How many moles of iodine, I2, are required to react with 0.429 moles of aluminum according to this reaction? Okay? So what you have here, this is AlI3, right? So if you have 0.49, let me see if, so if you have 0.429 moles of this, you have the molar ratio is 3 to 2, right? You have 3 and 2 here. So that means that you will need 0.644 moles of iodine. Okay? Now, the moles of C3H6 or butane yields what moles of carbon dioxide and how many molecules of carbon dioxide. Okay, and I'll let you solve that particular problem. Essentially, you use the same type of information. The molecular weight here is 3 times 12 plus 8 times 1. 3 times 12 is 24 plus 8 is 30. Is 32. Okay? And then if to have a balanced equation, you first have to write out the balanced equation. And then you'll know how many moles of this give you the number of moles of this. So that would be 3 of these to give you 1 mole of this yields 3 of these, right? Okay. And so you would have 1 mole here and 3 moles here. Okay, so that would be 3 times Avogadro's number to give you a total number of molecules. What mass of sodium hydroxide is required to produce 16 grams of magnesium hydroxide here? Okay, and here what you have is 16. The molecular weight of magnesium hydroxide is 53.3 grams. And then your molar ratio in the reaction is 2 moles of this to 1 mole of this. And your molecular weight of sodium hydroxide is 40 grams per 1 mole. So 16 divided by 15.3 times 2 times 40 gives you 22 grams of sodium hydroxide. And this type of a chain type of conversion allows you to convert the mass to the number of moles by this factor right here. Then the moles, you get the number of moles here because of what the coefficients are in the equation. And then you multiply that by the molar mass of this to give the gram.